For the first 3 videos in this series, we sat at the philosophical and ethical altitude. We asked what AI is, what it can never be, and what happens when emerging technologies push inside the body and brain. Today, I want to come down to the ground level. I want to look under the hood of the most powerful AI systems on the planet right now. The systems most of us are actually using: ChatGPT, Claude, Gemini, Llama, Mistral, large language models, LLMs. Now, today's aim is demystification, because much of the public conversation about AI is confused. People talk about large language models as if they were thinking and reasoning, understanding, or intending the way human beings do. Once we look at the basic architecture, that mystery starts to dissolve. A large language model is not a mind. It is not a person. It is not a moral agent. It does not have consciousness, intention, self-understanding. We've spent 2 videos defending those claims philosophically. Today, I want to show you why they hold up technically as well. An LLM is also not magic. It is a very large, statistical, and computational system trained on enormous amounts of text and other data to predict and generate sequences of symbols. So that means today, what we're going to be doing is looking inside the machine. Conceptually, we'll discuss what an LLM is, what tokens are, what tokenization does, why data matters so much, how pre-training works, what autoregressive language modeling means, why transformers are central, how these systems are evaluated, and how post-training methods like supervised fine-tuning and reinforcement learning from human feedback turn a raw next token predictor into something that behaves like a helpful assistant. By the end of this video, my goal isn't that you become an engineer. The goal is that you become philosophically and socially literate about LLMs. You should be able to understand the basic pipeline behind a ChatGPT-like model and evaluate claims about these systems more critically. So let's do a quick recap. In earlier videos, I defined artificial intelligence in a simple way. AI systems take in data, process it through algorithms, and produce outputs. The definition is basic, but it's useful because it strips away the mythology. AI is not a spirit inside a machine. It is not a hidden mind trapped in code. It is a system that transforms inputs into outputs through computational procedures. Large language models are a specific kind of AI system. They are designed to process and generate language. More precisely, they learn patterns and sequences of tokens, where tokens are units of text, words, parts of words, punctuation marks, or other symbolic fragments. And the reason LLMs feel so different from older forms of AI is that language is deeply connected to human intelligence. We use language to explain, reason, joke, argue, confess, imagine, remember, teach, pray. When a system produces fluent language, we are naturally tempted to attribute thought to it. This is one of the most powerful sources of confusion in the entire field. So keep that distinction clear. An LLM can generate text that looks thoughtful without itself thinking. It can generate an argument without believing that argument. It can answer a moral question without having moral awareness. It can describe suffering without suffering. It can simulate a conversation without being a conversational subject. Now you can ask, why does that matter philosophically? Well, Because if you understand how the systems produce language, you are less likely to confuse fluency for understanding. The central idea behind an LLM is this: it is trained to predict what comes next in a sequence. That's the basic engine. Given a context, it estimates what token is likely to follow. It does this again and again, one token at a time, until it produces a full response. And that sounds simple, and in one sense it is. When this simple objective is scaled to enormous datasets, enormous models, and enormous computing systems, the result is surprisingly powerful. So, what exactly is a large language model? An LLM is a machine learning model trained on large-scale text data to predict, generate, transform, or analyze language. The word large refers to several things at once: large datasets, large numbers of parameters, large computational systems, often large deployment infrastructures. A parameter is a learned numerical value inside the model. Think of parameters as the internal adjustable settings the model uses to transform inputs into outputs. During training, the model updates these parameters so that it becomes better at predicting language patterns. But be careful with metaphors here. Parameters are not memories in the ordinary human sense. They are not beliefs. They are not concepts stored like books on a shelf. They are numerical weights distributed across a mathematical system. The model does not contain a little library inside it. It contains a very large network of learned statistical relationships. When we call these systems language models, we mean they model probability distribution over sequences of language. In simpler terms, they learn which kinds of tokens tend to appear together, in which order, in which context, and with what relationships. They learn grammar, style, genre, factual associations, patterns of explanation, patterns of reasoning, and patterns of human conversation. And it's crucial to be precise here. They learn these as patterns. Whether they understand those patterns is a different philosophical question. In this series, we have repeatedly distinguished between behavior and interiority, between output and understanding, between simulation and consciousness. That distinction remains essential here. An LLM is best understood as a predictive language engine. It takes a sequence of tokens as input, transforms that sequence through layers of computation, and returns probabilities for possible next tokens. The final output we see is the result of repeatedly sampling from those probabilities. That is the heart of the system. Example of large language models include, as we mentioned, ChatGPT style models, Claude, Gemini, Llama, Mistral, and many others. Some are proprietary and they're offered through commercial platforms. Others are open weight or open source to varying degrees. Some are designed primarily for chat, others are designed for coding and translation, summarization, search, tutoring, scientific tasks, or multimodal work involving text, images, audio, and video. Beneath the branding, many of these systems share a common conceptual structure. They are trained on large datasets. They rely heavily on transformer architectures. They use tokenization to convert language into units of computer that can be processed. They learn through prediction objectives during pre-training. They are then adjusted through post-training to behave more helpfully, safely, and conversationally. And it's important to distinguish a base model from an assistant model. A base model is trained primarily to continue text. If you give it the beginning of an essay, it may continue the essay. If you give it a poem, it may continue the poem. If you give it code, it may continue the code. It has not necessarily been trained to behave. like a helpful assistant. It is, in effect, a text continuation engine. An assistant model has usually gone through post-training. It has been trained to follow instructions, answer questions, refuse certain requests, maintain a helpful tone, and align more closely with user expectations. ChatGPT-like systems are not merely pre-trained base models. They are base models that have been adapted into conversational agents through further training. This distinction matters because when we interact with a chatbot, we are not simply seeing raw language modeling. We are seeing language modeling shaped by instruction tuning, preference training, safety training, product design. So when we ask, how does ChatGPT work? The answer has two big parts. First, pre-training, where the model learns general language patterns, and then second, post-training, where the model is shaped into a useful assistant. But before we move into the technical pipeline, let me give you a simple mental model. Imagine you are reading a sentence. The student opened the book and began to... ... right? Ellipses. If I ask you what word comes next, you might say read. You might also say study, or write, or think. Some continuations are more likely than others. The student opened the book and began to swim is grammatically possible, but contextually it is unlikely. A language model does something structurally similar, just at enormous scale and with tokens rather than necessarily whole words. Given a context, it predicts what is likely to come next. Then it adds that token to the context and predicts the next one, then the next one, then the next one. Over time, these next token predictions become paragraphs and essays and answers and stories and code or dialogue. Now, some people may object. They may say, surely there must be more than next token prediction. These systems solve problems, they write arguments, they explain concepts, pass exams. And the answer is yeah. Yep. The behavior can become very sophisticated. The basic training signal is still prediction. The surprise of large language models is that predicting language at scale forces the model to internalize many patterns of the world as represented in language. To predict legal writing, it must learn patterns of legal reasoning. To predict philosophical writing, it must learn patterns of philosophical argument. To predict code, it must learn patterns of programming. To predict dialogue, it must learn patterns of conversation. And again, here we have to be precise. The model learns patterns that are useful for generating appropriate continuations. Whether that equals understanding is precisely the question we should resist answering too quickly. The Apple paper titled The Illusion of Thinking, I mentioned in my very first video, pulled this distinction apart empirically. Even when handed the complete recursive algorithm for Tower of Hanoi as a sketchpad, frontier reasoning models collapsed at the same complexity points. The limit wasn't in strategy discovery. The limit was in insight, the capacity to grasp a procedure as one thing applied iteratively. That's exactly what Lonergan calls level 2 of consciousness, the act of understanding. And it's exactly what a pattern matcher, no matter how large, lacks. This is why LLMs are both impressive but also dangerous. They're impressive because next token prediction at scale produces emergent looking capabilities. But they are dangerous. They're dangerous because fluent language can make us overestimate what is happening inside the system. Now, let's discuss one of the most important components of the entire system: data. If there is one principle you should remember, it's this: large language models are shaped by the data they are trained on. Data is not just fuel, it is formative. It influences what the model can say, how it says it, what assumptions it reproduces, what language it handles well, what cultures it represents, what stereotypes it may learn, what factual associations it contains, and what blind spots it inherits. Training data for large language models typically includes large amounts of text from many sources, including books, websites, articles, forums, code repositories, encyclopedic material, technical documentation, academic writing, conversational data. The exact composition varies by model and developer, and in many cases, it's not fully public. Data collection is never neutral, exactly for that reason. Decisions must be made about what to include, what to exclude, what to filter, what to prioritize, which languages to represent, which sources to trust, which kinds of harmful or low-quality content to remove. And this links directly to our earlier discussions on value-ladenness. A dataset is not merely a technical object. It is a cultural artifact. It reflects social histories, inequalities, biases, exclusions, and priorities. If a model is trained mostly on English language internet text, it will represent English language patterns better than many other languages. If its data contains stereotypes, the model may learn those associations. If some communities are underrepresented, the model may perform poorly on their linguistic or cultural context. If data is scraped without consent, questions of ownership and privacy, and of course exploitation arise. So before we ever reach algorithms, we are already doing ethics. Data curation is a moral and political activity as well as a technical one. Now, the data pipeline for training an LLM usually involves several stages as well. First, data is collected, and that may involve web crawls, licensed datasets, public domain material, code data, academic texts, and other sources. In some cases, developers also use data generated or reviewed by humans for specific training purposes. Second, the data is cleaned. Cleaning may involve removing duplicates, removing corrupted text, filtering spam, excluding malware, reducing personally identifiable information, removing some kinds of harmful or illegal content. Third, the data is processed into a format suitable for training. This includes tokenization, which we will discuss in detail shortly. Raw text cannot be fed directly into a neural network in the way humans read it. It must be converted into numerical representations. Fourth, the data set may be mixed or weighted. Not all data is treated equally. A developer might decide to include more code, more scientific text, more dialogue, more multilingual material, or more high-quality educational content. These choices shape the model's capabilities. Fifth, the model is trained on this data through a prediction task. It repeatedly sees sequences of tokens and tries to predict the next token. Each mistake produces an error signal. The system uses the signal to update its parameters. From a philosophical perspective, this should already make us cautious. Why? The model is not born from pure reason. It is trained from human-produced traces. It learns from what we have written, argued, recorded, uploaded, documented, disputed. In a strange way, LLMs are mirrors of collective textual culture. But they are distorted mirrors. They compress, recombine, and probabilistically reproduce patterns. They do not preserve context the way human memory does. They do not know the moral significance of what they repeat. They do not distinguish the truth from falsehood in the human sense. They learn distributions, not wisdom. So, it makes sense at this point to talk about evaluation. In machine learning, evaluation means asking, how do we know whether the model is good? And good can mean many different things. Good can mean good at predicting the next token, good at answering questions, good at coding, good at reasoning, good at being safe, good at being honest, good at refusing harmful requests, good at explaining uncertainty. Different evaluation measures measure different things. During pre-training, for example, one common measure is loss, which measures how wrong the model's predictions are. A related measure is perplexity, which I'll come back to. Lower perplexity generally means the model is better at predicting a given text sample. When models become assistants, evaluation becomes much more complicated. We may evaluate factual accuracy, helpfulness, harmlessness, reasoning quality, instruction following, robustness, calibration, bias, toxicity, privacy risk, and resistant to misuse. These are benchmark datasets where models answer standardized questions. There are human evaluators there where people compare the outputs. There are red teaming exercises where testers try to make the model fail or produce harmful content. There are domain-specific evaluations for law, medicine, programming, mathematics, and education. No evaluation is perfect. Benchmarks can be gamed. Test data can leak into training data. A model can perform well over a benchmark and still fail in real-world interaction. A model can sound confident while being wrong. A model can produce a pleasing answer that is simply not true. This is why LLM evaluation is not a purely technical matter. It is also normative. We must ask, what do we value in the system? Accuracy, creativity, safety, transparency, usefulness, fairness, epistemic humility. Different priorities will lead to different evaluation practices. Now, before we get to transformers and pre-training, we need to talk about systems. When people think about LLMs, they can often imagine the model, as if that model were a single object sitting on a computer. In practice, building and deploying large language models requires massive systems. A system includes hardware, software, data infrastructure, training pipelines, distributed computing, storage, networking, optimization tools, monitoring, and deployment platforms. Training a frontier-scale model may require thousands of specialized chips working together for weeks or months. Even smaller models require very careful engineering. The system must move enormous amounts of data. It must coordinate computation across many machines. It must handle failures. It must store checkpoints. It must track experiments. It must evaluate immediate versions. It must manage energy, cooling, cost, and infrastructure constraints. So when we talk about training an LLM, we should not imagine a laptop quietly learning from the internet. We should imagine an industrial-scale computational operation. LLMs are not only algorithms, they are infrastructures. And this has ethical implications. Large-scale training consumes energy and resources. It concentrates power in organizations that can afford the necessary compute. It creates dependency on specialized hardware, supply chains. It risks and raises very important questions concerning environmental costs, economic inequality, labor, data access, and institutional control. So in other words, the systems component is not a technical footnote. It is part of the social reality of AI. If data shapes what a model learns, systems shape who can build it, and that has consequences for power. In Magnifica Humanitas, Pope Leo XIV makes the point in stark terms. The encyclical notes that in the digital context, control over platforms, infrastructure, data, and computing power often does not rest with states. It rests with major economic and technological actors. These entities effectively set the conditions for access. They determine the rules for visibility. They shape the very possibilities for participation. And this is no small footnote then. It's a structural shift where power now lives. The material infrastructure of AI shapes the ethics for AI. A model is not just an abstract mathematical entity. It's embedded in institutions, servers, supply chains, labor practices, energy systems, regulatory environments. So that means that understanding LLMs requires more than understanding neural networks. It requires understanding the entire socio-technical system in which they are built and used. So now that we've explained that, we can move to the architecture that made modern LLMs possible, the transformer. Most contemporary LLMs are based on transformer architectures. What are these transformer architectures? Well, the transformer was a major breakthrough because it allowed models to process sequences of tokens in a powerful and scalable way, especially through a mechanism called attention. Before transformers, many language models relied on architectures that process text sequentially. This made it harder to capture long relationships. For example, in a long paragraph, a word at the end may depend on something much earlier. Traditional sequence models often struggled with this at scale. Transformers changed the situation by allowing the model to relate tokens to one another flexibly. Instead of reading only one word after another in a narrow chain, the model can compute relationships between many parts of the input sequence at once. And the central idea is that words, or more precisely tokens, do not have meaning in isolation. Their meaning depends on context. The word bank means something different in riverbank and central bank. The word light means something different in light suitcase, light bulb, light of truth. A model must therefore learn contextual relationships. And transformers are powerful because they build contextual representations. Each token is transformed in relation to other tokens. The model does not just see tokens as isolated symbols. It learns how each token matters given the surrounding sequences. And this is why transformers are important for language. Language is relational. Meaning depends on context. Attention mechanisms help models represent context. And again, this does not mean the model understands in the human sense. No. It does mean, however, that the model can learn very powerful statistical representations of linguistic context. Attention is a mechanism that allows the model to weigh the relevance of different tokens when processing a given token. Imagine the sentence, the doctor spoke to the patient because she was worried. Okay? Who does she refer to? The doctor? The patient? The answer depends on context. Humans use semantic understanding, background knowledge, and pragmatic reasoning. A transformer does not understand as we do. Attention helps it model which tokens are relevant to resolving such relationships. The phrase self-attention means the model compares tokens within the same sequence to one another. Each token can attend to other tokens and gather information from them. This produces richer contextual representations. So in simplified terms, attention asks, when interpreting this token, okay, which other tokens in the context matter most. A transformer consists of many layers of such operations. Early layers may capture simpler patterns. Later layers may represent more abstract or task-relevant patterns. The model gradually transforms raw token representation into complex, contextual representations that allow it to predict the next token. This is one reason LLMs can appear so flexible. The same architecture can learn grammar, style, factual associations, code syntax, conversational patterns, and forms of reasoning, because all of these can be represented as relationships among tokens. Now, we should stay disciplined here. Attention is not human attention. It is a mathematical mechanism. It does not involve awareness, does not involve care, does not involve intentional focus. The word attention is metaphorical. Now that we've explained attention, we can transition to pre-training. Pre-training is the first major stage in building a ChatGPT-like model. It's where the model learns broad patterns of language from large datasets. During pre-training, the model is not yet a polite assistant. It is learning to model language. The basic goal is simple. Predict the next token. Take a sequence of text, hide the next token, ask the model to guess it. Compare the guess to the actual token. If the guess is wrong, adjust the model's parameters slightly so that the next time it does better. Repeat this process billions or trillions of times across enormous datasets. This is called language modeling. The model learns a probability distribution over possible next tokens given previous tokens. Over time, this trains it to generate plausible continuations of text. For example, if the model sees Paris is the capital of, it should assign a high probability to France. If it sees the argument is valid if, well, it should learn patterns associated with logic. If it sees def function underscore name in code, it should learn likely programming continuations. This may seem like mere autocomplete, and in one sense it is. AI at scale, right? Autocomplete becomes surprisingly powerful. The reason is that language contains compressed representations of knowledge, reasoning, culture, practice. To predict language well, the model must learn many patterns that correspond to structures in the world. This also means that the model's knowledge is derivative. It comes from text. It is mediated by representation. It is not experience. The model has never seen Paris. It has never suffered injustice. It has never conducted a scientific experiment. It has learned textual patterns about these things. Pre-training gives breadth. It gives the model general linguistic competence. It does not automatically make the model truthful or safe or obedient or helpful. Now, let's define language modeling a little bit more explicitly here. A language model assigns probabilities to sequences of tokens. Given a context, it estimates how likely different continuations are. Suppose the context is, the cat sat on the model might assign high probability to mat, floor, chair, or sofa. It would assign low probability to democracy or photosynthesis, unless the context were unusual or poetic. The model is not selecting from a dictionary by meaning in the human sense. It is calculating probabilities based on patterns learned during training. Language modeling, therefore, can be used in different ways. Some models are trained to fill in missing text, others are trained to predict the next token. The type most relevant to ChatGPT-like generation is autoregressive language modeling. Now, what does that mean? Autoregressive means that the model generates output one step at a time, using its own previous output as part of the context for future outputs. It predicts token 1, then token 2, then token 3. Each new token depends on tokens that came before. This gives the model a kind of sequential unfolding. A full answer isn't produced all at once. It is generated token by token. This matters because it explains both fluency and failure. The model may begin a sequence in a plausible way and then continue based on its own previous words. If it makes an early mistake, that mistake can help shape what follows. If it drips into misleading frame, for example, later tokens may continue to drift. So generation is dynamic. It isn't the retrieval of a fixed answer from a database. It is a probabilistic unfolding of text. So if you've ever wondered why prompts matter so much, this is why. The prompt is the initial context. It shapes the probability distribution of what comes next. A vague prompt produces a wide range of possible continuations. A precise prompt narrows the space. A misleading prompt can steer the model toward error. A well-structured prompt can help the model produce a more useful answer. This also explains why models can be sensitive to wording. If you phrase the question differently, you change the context, and therefore you change the probabilities. The model does not access meaning in the stable human way. It responds to patterns in the token sequence. So, talk about tokens. Now we come to tokenization, one of the most important but least understood parts of LLMs. Humans see text as words, sentences, and meanings. Computers need numbers. A language model cannot directly process the sentence as you see it on a page. The text must first be broken into tokens and converted into numerical IDs. A token, as we mentioned, may be a whole word, part of a word, punctuation, white space, or even smaller units depending on the tokenizer. For example, the word unbelievable might be one token in some systems, or it might be split into pieces such as un and believe and then able. A common word may be one token, a rare word may be split into several tokens. And tokenization matters because the model's world is made of tokens. It predicts tokens, not directly concepts. When you type a prompt, the system tokenizes. When it generates a response, it generates tokens. The length of the context window is usually measured in tokens, not in words. This also explains why models sometimes behave strangely with spelling or counting letters, rhymes, or unusual names. The model may not see the text as we do. It sees token units, a word that looks simple to us but may be split into unexpected pieces. For philosophy students, this may be interesting, but tokenization is a useful reminder for them. The system does not encounter language as a human subject does. It does not hear tone or intention or embodiment or shared social meaning. It receives symbolic fragments encoded as numbers. So let me walk you through the tokenization process briefly. Suppose the sentence is, consciousness is not computation. The tokenizer breaks this string into tokens. Depending on the tokenizer, it might produce tokens corresponding roughly to consciousness, is, not, and computation, plus punctuation or spacing. In another system, consciousness might be split into even smaller pieces. Each token is assigned an ID number from the model's vocabulary. The vocabulary is the set of tokens the model can recognize and generate. A token might correspond to, for example, ID 14573, another to 318, another to 407, and so on. The specific numbers are arbitrary. The mapping is fixed for the tokenizer. Then those tokens are converted into embeddings. An embedding is a vector, a list of numbers representing the token in a mathematical sequence, right, in that space. The vectors are what the neural network actually processes. At first, embeddings are not meaningful. During training, the model learns useful representations. Tokens used in similar contexts may end up with related representations. This is mathematical similarity. It's not human meaning in the full sense. Tokenization also affects multilingual performance. Languages with writing systems or morphology poorly handled by the tokenizer may require more tokens for the same amount of content. This can make them less efficient or harder for the model to represent well, so tokenization can have fairness implications with it. Even here, at this apparently technical stage, values and social consequences appear. Which languages are efficiently represented, which names are fragmented, which scripts are disadvantaged. They are not merely engineering details. No, these shape access and performance. Now let's turn briefly to evaluation with perplexity. Perplexity is a common metric for evaluating language models, especially during pre-training. It measures how surprised the model is by a sequence of text. Lower perplexity means the model finds the text more predictable. Higher perplexity means the model is more uncertain or surprised. In simple terms, if a model assigns high probability to the correct next token, it has low perplexity. If it assigns how probability is correct to the high probability to the correct next token, it has high perplexity. Imagine two models predicting the sentence. The capital of Italy is Rome. A good model, after seeing the capital of Italy, should assign high probability to Rome. A weaker model might spread probability across many less appropriate options. The better model is less perplexed. Perplexity is useful because it gives a numerical measure of language modeling performance. It helps developers compare models during training. But perplexity still has its limits. A model can have low perplexity and still be unsafe. It can predict text well and still produce biased or harmful outputs. It can be fluent and still hallucinate. It can be statistically strong but ethically problematic. Perplexity measures prediction quality, does not measure wisdom or truthfulness or justice or responsibility. This is a general lesson about metrics. Metrics are useful, they are not the same as values. A metric captures what it is designed to capture. If we confuse the metric with the whole goal, we reduce the complexity of human evaluation to a number. So perplexity matters for pre-training. It is not enough, however, for evaluating a ChatGPT-like assistant. Now that brings us to post-training now. After pre-training, we have a base model. It has broad language capability. It can continue text. It may know many patterns. It may not reliably follow instructions. It may not know how to behave in dialogue. It may produce offensive or unsafe continuations. It may imitate whatever style appears in the prompt. It may complete a harmful instruction rather than refuse it. So developers use something called post-training. Post-training refers to additional training stages that shape the base model into something more useful, safe, and aligned with human expectations. The two most important post-training methods are supervised fine-tuning and reinforcement learning from human feedback. The former called SFT and the latter RLHF. The purpose of post-training is not to teach the model language from scratch. Pre-training already did that. The purpose is to shape behavior. This is similar to the difference between knowing a language and knowing how to participate in a particular social role. A person may know English but still need to learn how to write a legal brief, teach a class, conduct a medical interview, or answer politely a customer who is looking for support. Post-training teaches the model a role: helpful assistant, tutor, coding helper, summarizer, domain-specific tool. This is also where many ethical decisions become explicit. What should the model refuse? What tone should it use? How should it handle uncertainty? Should it be direct or cautious? Should it answer controversial questions neutrally? How should it respond to harmful requests? These are not only technical questions, but they're questions about values, norms, governance, and responsibility. Post-training is where the raw predictive engine is shaped into a social interface. So let's begin with supervised fine-tuning, or SFT. In supervised fine-tuning, the model is trained on examples of desirable behavior. Human trainers or data creators provide prompts and good responses. The model then learns to imitate those responses. For example, the training data might include a prompt like explain tokenization to a beginner. The good response would be tokenization is the process of breaking text into smaller units called tokens, etc., etc. The model compares its own output to the desired output and updates its parameters to become more likely to produce helpful answers like that. SFT is important because it teaches the model instruction following. A base model might simply continue the prompt. If you write, translate this sentence into Italian, the base model might continue with more examples or imitate the dataset. A fine-tuned assistant model is more likely to perform the task. SFT datasets often include many types of tasks: answering questions, summarizing text, writing explanations, generating code, refusing harmful instructions, maintaining tone, formatting instructions. SFT has limitations though. It teaches the model to imitate examples, but it may not capture all preferences. There can be many acceptable answers to a prompt. Human judgments may vary. Some answers may be technically correct but unhelpful. Others may be friendly but inaccurate. SFT alone may not optimize for nuanced human preference. Still, SFT is a crucial stage. It converts a general text predictor into an instruction following model. From a philosophical angle, this stage is interesting because it shows that the assistant personality is not spontaneous. It's trained. Helpfulness, politeness, refusal behavior, and conversational style are engineered outcomes. Now, let's discuss reinforcement learning from human feedback. Like I said, RLHF. RLHF is a post-training method designed to align model outputs most closely with human preferences. The basic idea is this: instead of only showing the model one correct answer, humans compare multiple modal answers and indicate which ones they prefer. For example, the model might generate 2 answers to the same question. Human evaluators decide which answer is more helpful, accurate, safe, or appropriate. These preferences are used to train a reward model. The reward model learns to predict which kinds of outputs humans are likely to prefer. Then, the language model is further optimized to produce outputs that receive higher reward scores. Quite unique. This is called reinforcement learning because the model is guided by a reward signal rather than simply imitating a fixed target response. So in simplified form, RLHF has 3 steps. First, collect human preference data. Second, train a reward model that predicts human preferences. Third, optimize the language model against that reward model. And this kind of reinforcement learning can make models more helpful and more conversational. It can reduce some harmful behaviors. It can improve instruction following and user satisfaction. But it also raises serious questions. Whose preferences are being used? What cultural assumptions do evaluators bring? What happens when helpfulness conflicts with truthfulness? What happens when users prefer confident answers even when uncertainty would be more honest? What happens when the reward model can be exploited? There's also a risk of producing models that sound better rather than are better. A model can become more polished, more agreeable, and more persuasive without becoming more truthful. The empirical research on this is now substantial. A 2025 paper from Anthropic and Truthful AI demonstrated something called subliminal learning. A teacher model with some behavioral trait can generate training data, like number sequences or code, that contains no explicit reference to that trait. A student model trained on that data nonetheless acquires that trait. Filtering the data for explicit references doesn't prevent transmission. Behavioral character in those systems propagates through channels developers cannot inspect. This is why post-training must be evaluated carefully. This kind of reinforcement learning is powerful, but it is not moral formation. It is preference optimization. After post-training, evaluation becomes broader. We no longer ask only, can the model predict text? We ask, can the model act as a reliable assistant? This includes many evaluation dimensions. Helpfulness, right? Does the model answer the user's question? Truthfulness, does it avoid fabricating facts? Harmlessness, does it refuse dangerous or abusive requests? Robustness, does it behave well under adversarial prompts? Fairness, does it avoid discriminatory patterns? Calibration, does it express uncertainty appropriately? Instruction following, does it obey constraints? Reasoning, can it solve multiple step problems? Domain competence, can it perform well in areas like law and medicine and education and coding or philosophy? Human evaluation is often necessary because many of these qualities cannot be fully captured by automatic metrics. Human evaluation is also imperfect, though. Evaluators disagree, standards vary, context matters. Some outputs look good, but contain subtle errors. This means that LLM evaluation remains an open and difficult problem. And here's where the deepest empirical findings of the past 2 years matters. A 2026 paper from Apple identified what the researchers called refusal neurons, individual neurons in LLMs that gate whether a model expresses harmful knowledge. Suppress a single refusal neuron without any training or prompt engineering, the model's safety alignment collapses. Across 7 different models from 1.7 billion to 70 billion parameters. Think about what that tells us. The refusal we see the moment the model says, I can't help with that. It looks from the outside like moral judgment. From the inside, it's a thin, localized gate any sufficiently skilled interpreter can flip. There is no network of considerations being weighed. There is no act of conscience. There is a switch. This composes with the illusion of thinking result on reasoning collapse, and with the subliminal learning result on character transmission into a single convergent picture. The frontier of capability is narrower and more brittle than public reporting suggests. And the kind of safety we are building into these systems is not the kind of Lonerganian person would call genuine moral judgment. For a series like this one, the lesson is broader. The quality of an LLM is not a single thing. There is no one number that tells us whether a model is good. A model can be strong in one domain and weak in another, helpful and too compliant, safe and overly cautious, fluent and false, creative and unreliable. So when someone says, this model is better, we should ask, better at what? For whom? Under what conditions? And according to what values? This is the responsible innovation question applied directly to LLMs. So let me draw the lecture together. A ChatGPT-like model is built through a sequence of stages. First, data is collected, cleaned, filtered, and processed. This data is the cultural and linguistic foundation of the model. Second, the text is tokenized. Language is broken into tokens and converted into numerical representations. Third, a transformer-based model is pre-trained through language modeling. It learns to predict the next token across enormous amounts of data. Fourth, the base model is evaluated using metrics such as loss and perplexity, along with benchmark tasks. Fifth, the model undergoes post-training. Supervised fine-tuning teaches it to follow instructions, and reinforcement learning from human feedback or related preference methods shape it towards human-preferred behavior. Sixth, the final assistant is evaluated for helpfulness, safety, accuracy, robustness, and other criteria. That is the basic pipeline. The philosophical lesson is just as important. LLMs are not magic. They're not persons either. They are not conscious. They are not moral agents. They are large-scale statistical systems trained to model and generate language. Their fluency is real. Their usefulness is real. Their risks are real. Their interiority is not. They do not know what they say in the way we know what we say. They do not understand truth as a norm in which they are responsible. They do not care whether they help or harm. They do not possess wisdom. They are tools built from data, algorithms, systems, and human decisions. And because they are tools, responsibility belongs to us, to designers, developers, companies, regulators, educators, users. The central ethical question is therefore not whether LLMs will become human. The central question is how human beings will use, govern, trust, depend on, and perhaps be reshaped by these systems. So the point of demystifying LLMs is not to dismiss them. They are powerful. They will continue to shape education, work, media, research, and social life. The more powerful a technology becomes, the more important it is to understand it clearly. Confusion leads either to fear or to idolatry. Understanding allows responsible judgment. In the next video, we'll take what we've learned today and follow it into the public sphere. If LLMs generate plausible language without understanding, and if synthetic media can produce evidence without witness, what happens to journalism and education and politics and the very possibility of shared truth? That is the territory of misinformation, deep fakes, and epistemic trust. Until then.